Alright, I decided to make this video after I'd already started working on this, so I'm already a couple of steps ahead of you here. Now, if you watch the video on that NCR cash register, the electronic one, that is, you would have seen me pull this beast out. This is the enormous power supply that came out of the thing, and it is, well, look at it, it's enormous. It's also extremely heavy. And I have not a freaking clue right now if it works. Other than, well, after a bit of cleaning, it looks a lot better. It does a fair bit of, or it does some regulation here. I'm pretty sure printer AC here, that's going to be just regular AC that's passing through it. But I'm almost certain that it is a linear power supply. Just given by the fact there's this massive hunker of a transformer there, and there's these enormous capacitors here, and while there is one printed circuit board in here, seems to be primarily used for regulation, and that's about it. It doesn't seem that bad itself. There's a few transistors, I believe, there. Or are they? No, those will be regulator. You know what? Actually, let's just search this up right now. Can I? What are the date codes on this? 1974, week 27. 6 dash... Oh, right. These all contain NCR part numbers, so I don't immediately have a cross-reference for it. Anyways, once it cleaned up, it didn't look too bad. I mean, sure, this power supply has seen a bit of abuse. Q7, this resistor right here, got toasty, but it does still read fine. These two lytics here, I haven't actually gotten to that, but that's because I'm currently working on these giant caps right here. And as you can see, one's already been disconnected because I've been playing with it. So this is a Sprague or Sprague electrolytic capacitor. It is rated for 25 volts DC, 30,000 microfarads, which is a lot. It is date coded, I believe, to 1974, week 43, I believe, which makes it a rather old capacitor. And I don't have testing equipment that lets me check capacitance or ESR on something like this. So I had to do my more basic tests, which are, first you see what the resistance is across the terminals, and it came out to be substantially high. And then after that there, you bring in a voltage with an ammeter, and just bring the voltage up and see what it does. And I usually get to about 50%, and then I'll let it coast back down again. And then I went all the way, and I was satisfied with what I was looking at. And I disconnected the bleeder resistor here because these capacitors are just that scary. Attached to the bench and brought it up to 25 volts. Left it there for a while. Took it off. The leakage seemed okay. I had no way to properly measure it, but since we were such a low resistance, I had no reason to say that it was bad. And of course, it also passed the rattle test as well, so it's not dry either to the point where it's got crusties flying around. So I would consider this cap here a good reform candidate, reusable. It's not bulged, it's not like there's no leaks coming out of the vent plug right there. So this one here I'm going to say is good. Now I'm going to move on to this one here, and this one here, which I have not done yet. So let's just put this, can I even pull that one out? Okay, yeah, I can. And I'm just going to use a screwdriver in the side here to grab that screw and twist it a couple of times. Alright. That one's loose. Before I do that, let's take the other one and put it back in. Now, you see how I have four cables here and 4 terminals, but 2 of them are tied together with red. I know this one here is positive. positive is marked on this capacitor as well. So it's straightforward to reattach it again. I'll just put the screw back on there. And also reattach the bleeder resistor. I didn't verify the bleeder resistor resistance. It is a carbon. Those things like to drift up in resistance, but the fact it worked and it was visibly draining at a more accelerated rate when it wasn't attached to a load or of a small size, well, that was justified. Good for me. So I'm just gonna put that there. I'm gonna tighten the screw. Doesn't need to get too tight. There. Alright, and the same thing for this one. So, actually, let's take the positive side off first. And this is not me that labeled them. This is NCR, because NCR was great like that. Everything here is labeled. Everything has, like, even for the additional regulators that are going on over here, like, these terminal blocks here are all labeled. Like, everything is labeled. It's beautiful. Really well done. Really well built. Put you back in there. Go. Red zip tie, red tie. On this side here, yeah, we can do this. So I'm just gonna pop that off. I can actually put that back on there. So I all know where that all is. And there's the cap. And this one here has a rating of probably the same thing. Ta-da! Yep, 30,000 microfarads, 25 volts DC. Okay, let's do some evaluation here. Mainly because I'm being extremely cheap, and if I don't have to buy new capacitors, I'm not going to. Plus, it's a cash register. I'm not spending a ton of money on this thing. Can you see that there? Yeah, it's out of focus, but it's close enough. First off, I just reconnected that resistor. Now I have disconnected again. Because otherwise, this is going to completely screw with my resistance test. And we're going to set it to 20 mega ohms. Whoop! Don't do that. Okay, and oh, it's showing something. 2 mega ohms, still 0. Okay, no, it went up, and it's continuing to go up. That means the cap's charging. But 50, 60, 70, 80, 90, 100. So in a capacitor, it's okay to be seen. Yeah, and I just took right off there. It's okay in a capacitor. Wow, it really took off. There we go. It's okay to see the resistance go up in a capacitor while you have it connected like this, because it just usually it means that the cap is charging. And in this case here, I mean, it's still going up. We're at 13K. And still rising, which, okay, that's fine. It's unreformed. It could still be bad. We'll find that out in the next tests here. So, why am I turning that off? So, we're going to switch this over to voltage. And now I'm going to reattach the bleeder resistor because reasons. Or, yeah. Did I drop something? No, I didn't. Okay. Alright. Now, what I'm going to be attaching here is I have off to the side, let me twist the camera. Hello. You see this little baby right here? This is my bench power supply. It'll do up to 32 volts at 3 amps. Which isn't perfect per se, but that's good enough for a reform here, 25 volts. And I'm going to attach, are we off? Yes, we're off. Okay, so it's 0.6 volts. And I'm going to be watching, you can't see it over here, but it does have an ammeter on it. And as that voltage is added, I should see it gain a current draw and then go away as the cap charges. If it continues to rise or it stays consistent, we have a problem. Also, just, do a feely check on the cap at the same time. And here we go. And it looks predictable. Just keeping it down below 50 milliamps. And we'll bring it to 10 volts or within that ballpark. There we go. And what's the discharge rate like? Looks fine. Recharge. Okay, and it basically sprung right back up. Alright. We'll bring it up to 15 volts. And our current draw is on the chart, I believe now. Is it? There is a noticeable current draw of about 10 or 15 milliamps. Then again, it's just occurring to me right now, yes, of course there's a current draw. There's a bleeder resistor right there. So, and I'm not touching it because, terrifying. But I'm just trying to feel there's heat coming off it. No, it's not dumping heat yet. Alright, 14.95, and it seems happy with that, so I'm going to turn the power off and let it discharge. And that'll take a moment. And actually, if I keep it attached to the bench supply here, it'll also load that a little bit and pull it down internally. There. I feel a little bit more confident with this cap if it's even just at 2 1/4 volts. When I remove this, watch that be my famous last word. There we go. I'm just gonna swing that out of the way. Going to reattach that. And I've lost my other multimeter lead. Come on, there we go. Attach you on there. It's still 2.3, but this is promising. Now that bleeder resistor has been removed, like, it stayed solid. If I just touch that bleeder resistor, yeah, it goes right back down again. So that's a good sign. Okay, reattach it to the bench, and we'll bring it back up again. And really, you should be doing this reform over the course of like 30, 45 minutes, an hour, 2 hours if you really want to bring it up slowly. And I'm just doing this for the sake of, I don't care too much about this power supply. I'm fairly certain it's okay in the caps. But hey, you guys want to watch me do this, don't you? 6, 7. Yeah, now that that bleeder resistor is off there, like aside from the current increasing briefly when I bring the voltage up, there's no current draw. That's excellent. How about now? So we're back up to 15 volts, and it is like it's fine. There's no draw on that. So we're gonna go to 20. Still like no current. Now, of course, it could be drawing right now at the microamps, and I just can't see it. Right now, I'm just looking to see if it's going to be something that's going to catastrophically fail the moment it's given a real-time load. Well, I put it to 20 and it went over. There we go. Let's bring it up to 25. Oh, too far. There we go. 24.9. Doesn't seem warm. Like my current draw is like still showing like nil on this readout, so I'm not going to complain about that. I would honestly justify that this cap here, if I leave it to reform, it's good. It'll be fine. It'll be fine. Like it's got a 1974 date code, but so far I have nothing to indicate to me that it's a bad cap. No problem at all. Wonderful. And yeah, so I'm going to take it off the power supply and it should stop. So there we go. Actually, better test here. So I'm going to bring back up the voltage, put it at 25. And I'm going to take it off, and we should be maintaining that voltage. 2, 3, 4, 5, 6. Okay, so about 5 seconds per discernible tenth of a volt drop here. Like, you know what? That's fine. That's fine. I'm saying that's good. Okay, now I gotta. Where is my? There it is. Attach my ground to the bleeder, and I'm gonna let that pull down. I will be back in a moment. Right, okay, so that has bled itself back down to 0, so it's safe to remove this. And for those wondering, I will do a more prolonged reform of these caps later, after this video is recorded, but I don't think you want to be around here for hours watching a cap do basically nothing. As it just sits here and reforms with me blindly observing it, because again, I have no way to monitor the health other than it's not getting warm and it's not drawing an excessive amount of current. No need to tighten that, John. Okay, so you can just go back there and just as before, I can take these off. All right. Okay, and hang on a second. I think I hear my door. You know, it's funny how that works. You go to sit down and get focused on something, and people start pulling you away every time you were working on it. Alright, so I checked out this cap. You saw, just as much as I do, that it's probably a good cap. Now we have this one. Oh, this is going to be fun. I can't, there's dirt there. You know, let's just wait till the band gets removed. Fun. And alright, 68,000 microfarads, 40 volts DC. This is scary. Alright. And oh no, the harness is strapped in like that. Okay, this is gonna make my life a bit more difficult. Is there a way for me to unscrew that? Can I get a screwdriver in there? Oh, I see what I'm gonna have to do. Hold on, let me go grab another screwdriver. Alright, I don't want to undo it or cut any of this beautiful lacing that's gone on here. It's so well done. But I'm just gonna take a longer than normal screwdriver. I'm just gonna feed that through. What side is the positive? Okay, that side is positive. Let's take that side off first. So this cap here, and I just totally broke a label off. Oh well. This cap here is too large a voltage for my bench supply. So I'm only going to be able to go up to 32 volts, and then that's it. So we're just going to have to test it like that. Alright, and oh, sorry, my hair's in the way. Okay, that's out of the way. And have I, no, that's fine. There we go. Alright, I'm going to keep that bleeder resistor handy. Again, I have no doubts that that's good, so. And same thing as before, we'll go the other way around. Start at 200 ohms and see what it does. There we go. And again, same thing as before, up goes the resistance. And I'm just watching that take off. Oh, Jesus, there we go. Alright, and slowly sitting at 3.7 K, or 3.7 K ohms, which is not as good as the other cap, but it's still going up, so I mean, I'm still reserving. Alright. Now this time, all I'm going to do is keep the resistor there so I can pull it back down again, but okay, we'll just now bring the voltage on it. Are we off? We're off. Clip there, clip there. I'm going to switch over to DC volts and see what happens. Oh. Okay, 2 volts. Looks okay. It's jumpy, but that's because currently it's unreformed. But again, we still have like no current. And this looks fine. Do I even have a mirror? I don't even have a mirror to show you. Like, there's no point. Can I? No, right, because this multimeter here has a bad 2 amp fuse, so I can't even show you microamps or milliamps. And on that note there, I'm actually going to make a little addition to this video here. So I went and took that stupid fuse, this one here, 2 amp fuse in my multimeter. Yeah, that's taken care of now. And it's sitting here, the big cap is now reforming, and currently we are looking at 559 microamps of leakage current currently, and it's only been about 10 minutes, and it's still going down. So this is significantly better than I thought it was. It's not as leaky. This is why when you're using an analog meter to really try and do stuff like this, make sure it's a more precise scale, or get a half decent digital multimeter and that'll do it for you as well. Anyways, back to the video. Okay, 10 volts. We're still good on leakage. Still good. Still good. Clicking over. How are we doing here? All right, 17. Looks all right. Yeah, it's yeah, this is looking good. Oh, and we just rolled over, so there we go. And 21, 22, 23. We are beginning to pick up a leakage current, but it's still very small. On an unreformed cap, again, I will pass that off unless it remains after the reforming process. Alright, so we're 26 now. We're almost at our max. Okay, so that's as far as my course will go. Oh, and, oh wait, no, I can do it just this way. My fine adjustment, 28, 29, 30, 31.4. Okay, so not exactly 32 volts. This is as far as it will let me go. And that seems fine. What happens if I remove voltage? There is... Wow, that's actually dropping a lot faster. Alright, well this is going to have to incur more testing. But... that was just me reconnecting the lead, by the way. Okay, well... Alright, well I'll leave that to further testing. In the meantime, I am going to, again, disconnect that. We are going to then run our ground lead to our bleeder resistor, and I believe that's just going to pull it straight down for us here now. Yeah, that might actually take a while. Oh, unless am I doing this wrong? Yes, I am doing this wrong. Duh. There we go. Now, ugh. I'm gonna go sideways with this because it has teeth. There we go. Okay, yeah, and that's gonna pull it down. Okay, so Welcome to Ghetto Cap Reforming and Testing here with John. And I hope you enjoyed what you watched. And until next time, have a good one.